Okay, good morning. Happy Monday. Welcome back to the stream. Hope everybody had a fantastic weekend. We're going to just dive right in because that's the thing I do on this channel. It's no pre-work chat or anything like that. We just get right to it. So last week when we left our intrepid coders, what did we have? We had just finished, just log, singular. We'd done reading variables, so we can actually read variables out of. And how did I test it? I don't remember how I tested it. Fix that. Cargo run. Okay, so all we did was write some simple code. We have this breakfast locks file, which sets beverage to cafe au lait, sets breakfast to that, and then prints it. And we were able to run that and see that cargo run. Let's just run it again. And it prints it out. So we're able to see the variables, or to read the variables. We're able to do the assignment with strings, or sorry, addition with strings, and then print the result. So we actually have something that's almost working, is almost a real language. So now we're going to talk about assignment. So this is initialization, where we say var variable equals value. But to modify an existing variable is what we're going to talk about now. That's what assignment's all about. All right, let's dive in. Throughout this book, I've tried to keep you on a fairly safe and easy path. I don't avoid hard problems, but I try not to make the solutions more complex than they need to be. What does it say? Alas, other design choices in our bytecode compiler make assignment annoying to implement. If you recall, assignment was pretty easy in JLOX. Our bytecode VM uses a single pass compiler. It parses and generates bytecode. Yeah, I got to adjust my volume here. There we go. It parses and generates bytecode on the fly without any intermediate AST. As soon as it recognizes a piece of syntax, it emits code for it. Assignment doesn't naturally fit that. Consider menu.brunch of Sunday.beverage equals mimosa. In this code, the parser doesn't realize menu.brunch of Sunday.beverage is the target of an assignment and not a normal expression until it reaches an equal sign, many tokens after the first menu. By then, the compiler has already emitted bytecode for the whole thing. The problem is not as dire as it might seem. I remember having a similar problem with the JLOX thing, but we didn't emit bytecode. All we were doing is building up a tree, and then when we saw an equal sign, we said, oh, this is an assignment tree. And so this became the left-hand side of an assignment. So no code was emitted, but now we were emitting code for all of this. How do we turn it into an assignment? Look how the parser sees the example. There's a target expression, there's a field, there's a assignment operator, and then the value. Even though the .beverage part must not be compiled as a get expression, everything to the left of the dot is an expression with the normal expression semantics. The menu.brunch of Sunday part can be compiled and executed as usual. Fortunately for us, the only semantic differences on the left side of an assignment appear at the very rightmost end of the tokens, immediately preceding the equal sign. Even though the receiver of a setter may be an arbitrarily long expression, the part whose behavior differs from a get expression is only the trailing identifier, which is right before the equal sign. We don't need much look ahead to realize beverage should be compiled as a set expression and not a getter. Variables are even easier since they are just a single bare identifier before an equal sign. The idea then is that right before compiling an expression that can also be used as an assignment target, we look for a subsequent equals token. If we see one, we compile it as an assignment or a setter instead of a variable access or getter. We don't have setters to worry about yet, so all we need to handle are variables. All right, so we're going to modify in compiler named variable. We have this identifier constant, and now we're going to change this get global to either get or set, depending on whether or not we're going to match the equal sign, self match. Oh, is match, right? We have to do, right? Is that what I called it? Yes. Token type assign is what I renamed it. and then self-expression, and then self-emit bytes of set global. Oops. Else this. Right? And then, what was it? Oh, wow. It didn't take that away, huh? We don't have set global, obviously. So, okay, so everything works except for that part. In the parse function for identifier expressions, we look for an equal sign after the identifier. If we find one, instead of emitting code for variable access, we compile the assigned value and then emit the assignment instruction. That's the last instruction we need to add in this chapter. Okay, so in a chunk, we're going to say set global and put it down here as number 18. And there we go. Pretty straightforward. We do need to handle all this stuff. As you'd expect, its runtime behavior is similar to defining a new variable. So in VM, we have define global, we have get global. Let's put it right after here, I guess. Set global, opcode, set global. And what does this do? Read string, that's what this is doing, right? Read constant clone. I'm just trying to see how we can make it similar. If table set global's name peak 0, then table delete, runtime error, and defined variable something, and interpret error. Break. Oh, right. So I don't have table set. I have this global's insert. And this is just doing a peek. Where does it pop? The call to table set stores the value in the global variable table, even if the variable wasn't previously defined. That fact is visible in a REPL session, since it keeps running even after the runtime error is reported. So we also take care to delete that zombie value from the table. The main difference is what happens when the key doesn't already exist in the global's hash table. If the variable hasn't been defined yet, it's a runtime error to try to assign to it. Locks doesn't do implicit variable declaration. The other difference is that setting a variable doesn't pop the value off the stack. Here we go. Remember, assignment is an expression, so it needs to leave that value there in case the assignment is nested in inside some larger expression. Okay, so that's why we're doing the peek. So it's going to be similar to define. Oops. Let constant is equal to self read constant clone. If let value stir s equals constant, then instead of doing a pop, we're going to do let p equals self peak 0, self globals. Oh, okay. So now we're going to do it before we even assign it. We're going to use our cool entry feature of let's say it's Rust hash table Rust hash map entry, which I've looked at 100 times and I still don't have the syntax down for. And there's no or else method here, which is a shame because it'd be nice to run the error message handling code. But there's a way to how do we just get near occupied entry? Here it is. Oops. So if let entry occupied O equals self globals entry of S. If it's occupied, then we can assign it. We can say O dot, we don't want to remove it, we want to get mut. There we go. Get mut equals P. Can we do it that way? Else, we're going to find out if we can do it that way. Otherwise, we're going to report the runtime error, which looks like this. Self runtime error. Format bang undefined variable S. Just like that. And we're going to return that. And that's it. Okay, let's see if this works. Oh, I have to import the entry, right? I have to use the entry. Here it is. I guess we can combine them like this. Hash map entry. And then do we need to do anything with occupied? There we go. And we can't do that. Oh, we have to clone it. That's right. Just like up here, we had to clone it. And then we don't have this instruction, right? It's for disassembly. Okay. Add a dash of disassembly. There you go. For get global, change to set global. And get global, change this to set global. Is that all we have to do? I don't need to pass in the chunk because we already have that. So we're done, right? Well, not quite. We made a mistake. Take a gander at A times B equals C plus D. According to Locke's grammar, equals has the lowest precedence. So this should be parsed roughly like A times B is equal to, assigned to C plus D. Diablo says, who allowed it to be Monday? Talk to the time gods. Obviously, A times B isn't a valid assignment target, so this should be a syntax error. But here's what our parser does. First, parse precedence parses A using variable. After that, it enters the infix parsing loop. It reaches the star, calls binary. That recursively calls parse precedence to parse the right-hand side operand. That calls variable again for parsing B. Inside that call to variable, it looks for a trailing equals. It sees one and thus parses the rest of the line as an assignment. In other words, the parser sees the above code like A times the assignment of B to C plus D. We've messed up the precedence handling because variable doesn't take into account the precedence of the surrounding expression that contains the variable. Wouldn't it be wild if A times B was a valid assignment target, though? You could imagine some algebra-like language that tried to divide the assigned value up in some reasonable way and distribute it to A and B, and that's probably a terrible idea. If the variable happens to be the right-hand side of an infix operator or the operand of a unary operator, then that containing expression is too high precedence to permit the equal sign. To fix this, variable should look for and consume the equals only if it's in the context of a low precedence expression. The code that knows the current precedence is logically enough parse precedence. The variable function doesn't need to know the actual level, it just cares that the precedence is low enough to allow assignment. So we pass that fact in as a Boolean. Alright, so we still have 3 errors, and this is a mutable borrow business. Okay, so maybe what we do is we want to clone this here, right? Because what's happening is we have a pointer into this thing immutably, and then we try to grab a mutable reference to it, which the borrow checker doesn't like. We still have an issue here. Oh, help consider changes to mutable, so we can just say mut-o in there. Mute. And this S has type string, which does not imply, it does not implement the copy trait. We were able to do that just fine up here. So what's the difference between the one that's here? Oh, yeah. And it's not complaining about this one. Why is it okay with that one, but not with this one? because this is the same code, right? Oh, maybe because of this. No, that didn't help. Oh, because the entry takes. Do I have to clone this here? Come on. Yeah, that's annoying. I thought I was being all clever with this entry API, but in order to reuse S down here, we have to clone the S as the entry. Bleh. All right, but we still have this bug here. So in compiler, parse precedence, that's right there at the bottom. Okay, so after this, oh wait, what's going on here? I see expected expression reach. Oh, right, that's this thing here. All right, so before prefix rule, we're going to say let can assign equals precedence is less than or equal to, and what did I call them? Precedence assignment, which there isn't much. There's just none. So that's pretty straightforward. Okay, and then we pass in can assign here. Ooh, is prefix rule a... Oh, now it needs to be modified. The function signature needs to be modified. Because a prefix rule is something we get out of the table. Are we they're going to talk about that? Yeah, over here. Okay. Since assignment is the lowest precedence expression, the only time we allow an assignment is when parsing an assignment expression or top-level expression like an expression statement. That flag makes its way to the parser function here. So if we go to variable, can assign bool, and then we pass that down here, which passes it through a new parameter, can assign bool, and then finally uses it here. So if can assign and like that, and match token equal, and then expression. That's a lot of plumbing to get literally one bit of data to the right place in the compiler, but arrived it has. If the variable is nested inside some expression with higher precedence, can assign will be false, and this will ignore the equal sign even if there is one there. The named variable returns, and execution eventually makes its way back to parse precedence. Then what? What does the compiler do with our broken example from before? Right now, variable won't consume the equal sign, so that will be the current token. The compiler returns back to parse precedence from the variable prefix parser, and then tries to enter the infix parsing loop. There is no parsing function associated with equals, so it skips that loop. Then parse precedence silently returns back to the caller. That also isn't right. If the equal sign doesn't get consumed as part of the expression, nothing else is going to consume it. It's an error, and we should report it. Okay, so parse precedence. After we call the infix rule, if can assign and match, self is match token type assign, then we're going to say self error invalid assignment target. Right? With that, the previous bad program correctly gets an error at compile time. Okay, now we're done. Still not quite. See, we're passing an argument to one of those parse functions, but the functions are stored in a table of function pointers, so all the parse functions need to have the same type. Even though most parse functions don't support being used as an assignment target, setters are the only other one. Our friendly C compiler requires them all to accept the parameter. Flocks had arrays and subscript operators like array of index, and infix open bracket would also allow assignment to support array of index equals value. So we're going to finish off this chapter with some grunt work. First, let's go ahead and pass the flag to the infix parse functions. Actually, we don't need to worry about the infix ones, right? Because the infix ones, where did I define it? The infix ones just we can just say this prefix is the only one that takes it. Let's try doing it this way. And now it's going to complain about which ones. Oops, should be a comma. Ooh. Oh yeah, so I think that's simple enough, right? If we go to grouping, we just see Boolean like this. So we're talking about binary, literal, grouping, number, string, unary. So those are the only ones. So unary. Yes. So we can do this, bool. Number, literal, and unary. Okay, so if in literal, number, string, come on, did I get them all? Oh, really? Oh, right. We need to pass in something here that gets ignored. What if we change it to the other way around? Like that. Yeah. So if I look for all the unaries here, I can change this to compiler unary. And then we have number. Literal. Like that. Okay, did I get all those? Nope, and string. Compiler string. There, and then compiler variable. Okay, is that all? Oh no, here's binary up here. I missed binary. Okay. What am I still missing here? Okay, so this is where we need to do the we have to give it the lifetime, right? Why is this one? All the other ones are fine, but binary is not? Oh, because it's infix. Oh, man. Okay, so I do need to change all of them. Oops. Okay. Oh, and I need to add the... I didn't realize we use them for both infix and prefix. Okay. Oh, yeah, we use them all over here for infix. Compiler... binary. Incorrect number of function parameters. Didn't I change this to bool? I did. Right there. Oh, did I forget to change binary? Yeah, I did. Okay. One more. Ooh, we have to pass can assign. Actually, we just can pass false in that one, right? What does he do? Yeah, he passes can assign. Okay. All right. I think we're there. Phew. We're back to C program that you can compile, fire it up, and now you can run this. Okay. Cargo run. Breakfast. And it still works. Okay, we haven't broken anything, but we now are able to handle assignment syntax errors. A times B equals C plus D. Error at equal sign, invalid assignment target. Let's fix that before I commit the changes here. My G key sometimes is a little fussy. Okay, and we'll check in with clicky. We will git add source, git status, git commit -m. And what section was this? Wow, this is a big section. Okay, section 21.4, assignment. Not bad, not bad. Okay, what are the challenges? The compiler adds a global variable's name to the constant table as a string every time an identifier is encountered. It creates a new constant each time, even if that variable name is already in a previous slot in the constant table. That's wasteful in cases where the same variable is referenced multiple times by the same function. That in turn increases the odds of filling up the constant table and running out of slots, since we only allow 256 constants in a single chunk. The reason I paused there for a minute was because I don't think we do that in our version, because we're using the hash map. It's in the VM. Set constant. Set global. Right, we're just overwriting it here, and when we define the global, we're inserting it, so it's going to overwrite any previous version of it. So I don't think it's going to be a problem in this version of the code. In the Rust version of the code. Looking up a global variable by name in a hash table each time it's used is pretty slow, even with a good hash table. Can you come up with a more efficient way to store and access global variables without changing the semantics? When we get global, we have to grab the string and then look it up. What other If we don't store it by string, what if we convert it as we're compiling it, instead of storing the constant, instead of reading the string, if we know it's a constant, we can just use the index of the constant itself as a pointer into an array of globals. That'll make a sparse constants table, right? Because it'll be dependent on the order that it was inserted into the table. But it's an O of 1 lookup then, instead of O of looking up the hash table thing, or calculating the hash of the string. When running in the REPL, a user might write a function that references an unknown global variable. Then in the next line, they declare the variable. Lock should handle this gracefully by not reporting an unknown variable compile error when the function is first defined. But when a user runs a lock's script, the compiler has access to the full text of the entire program before any code is run. Here we can tell statically that oops will not be defined, but because there is no declaration that global anywhere in the program. Note that useVar is never called either, so even though the variable isn't defined, no runtime error will occur because it's never used either. Hang on, I gotta report a... how do I ban report? Self-harm, spam we go. There we go. Spam. Okay. Block this user. There we go. Done. Okay. Apologies for that. We could report mistakes like this as compiler errors, at least when we're running from a script. Do you think we should justify your answer? What other scripting languages do you know? So yeah, being able to tell that we never call this function would be neat. I mean, obviously be an enhancement to this thing is say, okay, we never generated a call opcode for it. Right? Each function. Well, we haven't gotten to that part yet, right? We don't define functions. We can also look to see if we generated any get globals on oops. We can also say get globals on the extended oops. That'd be able to tell us if we ever read it. So yeah, we could just store a little extra data with the globals as we encounter them and say which opcodes did we generate for each. And if this is printed without being set, we can say, okay, we did a bunch of gets on this, but we see 0 sets on it. So that sort of thing. But let's take a look at local variables. See this? We clean. We're clean. The last chapter introduced variables to CLOCs, but only of the global variety. There's probably some dumb think globally, act locally joke here, but I'm struggling to find it. In this chapter, we'll extend that to support blocks, block scope, and local variables. In JLOCs, we managed to pack all of that and globals into one chapter. For CLOCs, that's 2 chapters worth of work, partially because, frankly, everything takes more effort in C. But an even more important reason is that our approach to local variables would be quite different from how we implemented globals. Global variables are late bound in locks. Late in this context means resolved after compile time. That's good for keeping the compiler simple, but not great for performance. Local variables are one of the most used parts of the language. If locals are slow, everything is slow. So we want a strategy for local variables that's as efficient as possible. Function parameters are also heavily used. They work like local variables too, so we'll use the same implementation technique for them. Fortunately, lexical scoping is here to help us. As the name implies, lexical scope means we can resolve a local variable just by looking at the text program. Locals are not late bound. Any processing work we do in the compiler is work we don't have to do at runtime. So our implementation of local variables will lean heavily on the compiler. Representing local variables. The nice thing about hacking on a programming language in modern times is there's a long lineage of other languages to learn from. So how does C and Java manage their local variables? Why? On a stack, of course. They typically use the native stack mechanisms supported by the chip and OS. That's a little too low level for us, but inside the virtual world of CLOCs, we have our own stack we can use. Right now, we only use it for holding on to temporaries, short-lived blobs of data that we need to remember while computing an expression. As long as we don't get in the way of those, we can stuff our local variables onto the stack too. This is great for performance. Allocating stack for a new local requires only incrementing the stack top pointer, and freeing is likewise a decrement. Accessing a variable from a known stack slot is an index array lookup. We do need to be careful though. VM expects the stack to behave like a stack. We have to be okay with allocating new locals only on top of the stack. And we have to accept that we can discard a local only when nothing is above it on the stack. Also, we need to make sure temporaries don't interfere. Conveniently, the design of locks is in harmony with these constraints. New locals are always created by declaration statements. Statements don't nest inside expressions, so there are never any temporaries on the stack when a statement begins executing. Blocks are strictly nested. When a block ends, it always takes the innermost, most recently declared locals with it. Since those are also the locals that came into scope last, they should be on top of the stack where we need them. Step through the example program and watch how the local variables come and go out of scope. So this pops off when we end the scope. E goes on and then pops off, and then C pops off, and then B pops off, and we have A and F, and G, and then they all pop. This alignment obviously isn't coincidental. I designed locks to be amenable to single pass compilation to stack-based bytecode, but I didn't have to tweak the language too much to fit these restrictions. Most of its design should feel pretty natural. This is in large part because the history of languages is deeply tied to single pass compilation and to a lesser degree stack-based architectures. Locks is block scoping. Hi Bear, how are you? Locks' block scoping follows the tradition of stretching back to BCPL. As programmers, our intuition of what's normal in a language is informed even today by the hardware limitations of yesteryear. Okay, so it seems the stack will work for storing locals at runtime. We can go further than that. Not only do we know that they will be on the stack, but we can even pin down precisely where they will be on the stack. Since the compiler knows exactly which local variables are in scope at any point in time, it can effectively simulate the stack during compilation and note where in the stack each variable lives. In this chapter, locals start at the bottom of the VM stack array and are indexed from there. When we add functions, that scheme gets a little more complex. Each function needs its own region of the stack for its parameters and local variables, but as we'll see, that doesn't add as much complexity as you might expect. We'll take advantage of this by using stack offsets as operands for the bytecode instructions that read and store local variables. This makes working with locals deliciously fast. As simple as indexing into an array. There's a lot of state we need to track in the compiler to make this whole thing go, so let's get started there. In JLocks, we used a linked chain of environment hash maps to track which local variables were currently in scope. That's sort of the classic schoolbook way of representing lexical scope. For CLocks, as usual, we're going a little closer to the metal. We have a simple flat array of all locals that are in scope during each point in the compilation process. I guess we can have up to 256 locals. I guess what we can do for us is just use a vec for this. What's the difference between local count and scope depth? We have a simple flat array of all locals that are in scope during each point in the compilation process. They're ordered in the array in the order that their declarations appear in the code. Since the instruction operand we'll use to encode a local is a single byte, our VM has a hard limit on the number of locals that can be in scope at once. That means we can also give the locals array a fixed size. We're writing a single pass compiler, so it's not like we have too many other options for how to order them in an array. Okay. The local count field tracks how many locals are in scope, how many of those array slots are in use. We also track the scope depth. This is the number of blocks surrounding the current bit of code we're compiling. All right, so in here, in our compiler, right, we have parse rule, we have precedence. We can create a struct of, this is inside the compiler. Does that make sense? Because right now our compiler has the parser, the scanner, the chunk, and the rules. And I did that all because we don't have globals, or I'm not using lazy statics anyway. With all the mess they involve. So do I just throw the locals here? And there's this new struct called local, which we're going to have to define. Vec of local. And then we're going to have a scope depth. Scope depth, which is usize because it's going to be an index. Back in the compiler struct, the local count field tracks, right? Okay. Our Java interpreter used a chain of maps, right? So this time we'll simply number the variables at a level of nesting where they appear. 0 is the global scope, 1 is the first top level block, 2 is inside that. You get the idea. We use this to track which block each local belongs to, so that we know which locals to discard when a block ends. So local is going to be a token and a depth. I'm already smelling borrow checker problems. Struct, local, name, token, depth, usize. And this needs to be initialized, obviously. And scope depth of 0. Okay, so the warnings are just that we're not using any of them yet. Okay, we store the name of the variable. When we're resolving an identifier, we compare the identifier's lexeme with each local's name to find a match. Oh, so we're just going to scan O(n). It's pretty hard to resolve a variable if you don't know its name. The depth field records the scope depth of the block where the local variable was declared. That's all the state we need for now. This is a very different representation from what we had in JLOCs, but it still lets us answer all of the same questions our compiler needs to ask of the lexical environment. The next step is figuring out how the compiler gets at this state. If we're principal engineers, we give each function in the front end a parameter that accepts a pointer to a compiler. We'd create a compiler at the beginning and carefully thread it through each function call. So we're doing that, actually. Right? Because I've shoved it into the self. So it's already there. But that would mean a lot of boring changes to the code we already wrote. So here's a global variable instead. All right. So we get it through our compiler struct. In particular, if we ever want to use our compiler in a multi-threaded application, possibly with multiple compilers running in parallel, then using a global variable is a bad idea. All right. So we're already doing this, right? Because I put it in, and I'm not calling it compiler. I'm calling it what? Local, just vec of locals. And we're already doing this. The local count is just going to be the vec.len, and then the scope depth I've already set. When we start up the VM, we call it to get everything to a clean state. So we're already doing that. Our compiler has the data it needs, but not the operations on that data. There's no way to create and destroy scopes or add and resolve variables. We'll add those as we need them. First, let's start building some language features. Now we're on block statements. Before we can have any local variables, we need some local scopes. These come from two things, function bodies and blocks. Functions are a big chunk of work that we'll tackle in a later chapter. So for now, we're only going to do blocks. As usual, we'll start with the syntax. The new grammar we'll introduce is this. So we have a statement can be an expression statement, a print statement, or a block. When you think about it, block is a weird name. Used metaphorically, a block usually means some small indivisible unit, but for some reason the Algol 60 committee decided to use it to refer to a compound structure, a series of statements. It could be worse, I suppose. Algol 58 used begin and end statement parentheses. I'm glad we're using braces. Blocks are a kind of statement, so the rule for them goes in the statement production. The corresponding code to compile one looks like this. Begin scope, end scope. I remember that from JLOCs. Statement. So if it matches left brace, then we say self begin scope, block, self block, and self end scope. After parsing the initial curly brace, we use this helper function to compile the rest of the block. All right. fn block, not self. This is while not self check token type right brace and not self check token type EOF. Then what are we going to do? We're going to just call declaration self declaration, and then we're going to call self consume token type right brace, and then expect right brace after block. Oh, Rust might want me to put a double right brace on there. Oh, we don't have begin scope. We don't have end scope. Okay. It keeps parsing declarations and statements until it hits a closing brace. As we do with any loop in the parser, we'll also check for the end of a token stream. This way, if there's a malformed program with a missing closing curly, the compiler doesn't get stuck in a loop. Executing a block simply means executing the statements it contains, one after the other, so there isn't much to compiling them. The semantically interesting thing blocks do is create scopes. Before we compile the body of a block, we call this function to enter a new local scope. Begin scope. Self.current. Oh. This current. Wait a minute, I'm missing something here. Current is going to be the compiler. Right, so I just stuck it in here directly. And then we have end scope, which does the opposite. I was thinking the parser has previous and next. Yeah, self parser previous and self parser current. That's why I was hung up for a second there. Scope depth minus equals 1. Okay. So in order to create a scope, all we do is increment the current depth. This is certainly much faster than JLOX, which allocated an entire new hash map for each one. Given begin scope, you can probably guess what end scope does. So that's it for blocks and scopes, more or less. So we're ready to stuff some variables in them. All right, let's just check to see if everything builds. We're down to 4 warnings. That's fine. Usually we start with parsing here, but our compiler already supports parsing and compiling variable declarations. We've got var statements, identifier expressions, and assignment in there now. It's just that the compiler assumes all variables are global, so we don't need any new parsing support. We just need to hook up the new scoping semantics to the existing code. So we have var declaration, calls parse variable, which is constant, compile initializer, call define variable. Variable declaration parsing begins in the var declaration and relies on a couple of other functions. First, parse variable consumes the identifier token for the variable name, adds its lexemes to the chunk's constant table as a string, and then returns the constant table index where it was added. Then, after var declaration, compiles the initializer, it calls define variable to emit the bytecode for storing the variable's value in the global variable hash table. Both of these helpers need a few changes to support local variables. So in parse variable, here, so we have the consume of the identifier. Then we're going to call, before we do the identifier constant business, we're going to call declare variable. Yeah, so I had to split this into 2 for borrow checker rules. So I think all we have to do is say self declare variable here. And then say if self.scope depth is greater than 0, return 0. That's interesting. And then do this identifier constant. So first we declare, in quotes, the variable. I'll get to what that means in a second. After that, we exit the function if we're in a local scope. So we're not creating the global, I guess, right? Does that make sense? At runtime, the locals aren't looked up by name. There's no need to stuff the variable's name into the constant table. So if the declaration is inside a local scope, we return a dummy index table instead, returning 0. Over in define variable, we need to emit the code to store a local variable. So here's define variable. If self scope depth is greater than 0, return. So we don't do anything. Can I flip that? Or are we going to get more complicated? If I say this, that way you're saying if our scope depth is 0, then this is what we do. Otherwise, we don't do anything. This seems more natural to me in terms of programming. So likewise, do this. Right? I think I like this better. All right, let's do it this way, and then maybe it's going to make my brain hurt when we come back in a few days and say we have to change this. So over in define variable, we need to emit code to store a local variable. Over in local scope, it looks like this. But wait, what? Yep, that's it. There is no code to create a local variable at runtime. Think about what state the VM is in. It has already executed code for variable's initializer, or the implicit nil if the user omitted an initializer. And that value is sitting right on top of the stack as the only remaining temporary. We also know that new locals are allocated at the top of the stack, right where the value already is. Thus, there's nothing to do. The temporary simply becomes the local variable. It doesn't get much more efficient than that. The code on the left compiles to the sequence of instructions on the right. So var a is 1 plus 2, 1 to 2, and then we don't do anything. We set it to 3, and then b gets set to 4, and that's it. Okay, so what's declaring about? Here's what that does. Okay, let's declare a variable. Fn declare variable, and it returns nothing. If, here we go again. So if self scope depth, I'm going to do this again, is equal to 0, then we're going to add local. Let name is equal to self parser previous clone self add local name. Should I just pass it like that? And then we're going to have to figure out what add local does. This is the point where the compiler records the existence of the variable. We only do this for locals. So if we're in the top level global scope, we just bail out. Because global variables are late bound, the compiler doesn't keep track of which declarations for them it has seen. Right. We just throw it on the constant table. For local variables, the compiler does need to remember that the variable exists. That's what declaring it does. It adds it to the compiler's list of variables in current scope. We implement that using another new function. Okay. And it takes a name token and returns nothing. So we're going to create a new local onto the stack. Right. So all we're going to do is can I pass this in here? Instead of cloning it here, I can clone it onto the stack, right? Because all we're going to do is self local dot push of name dot clone, right? So that's what this translates into. Oh, and then yeah, our current depth is going to be the each local has to have its own depth, right? Yeah. So add locals is actually going to do let loc equals local of name, which is going to be name.clone, and then depth is just going to be self scope depth, right? And then we put, that's what we push. And so I don't want to clone this here. Can I do this self parser previous? Can I just pass that reference in without upsetting the borrow checker? So that's a shame. I don't want to have to clone it twice. I shouldn't have to clone it twice. But we are, yeah, and even, so I can't separate it like this because we're still borrowing it twice, right? Oops, we don't need that. Yeah, so the immutable borrow occurs here, and then we mutably borrow the locals. So one thing we could do is just use the ref cell, right? And we could just make this a ref cell. Right. That way add local can just contain a self, and we can just say borrow mute here. And then this becomes this. Yeah. That might be cleaner, I think, than trying to clone it twice. We're already cloning it once. I don't want to have to clone it a second time, right? So I think we can do it this way. This is pretty clean. We just have to remember every time we access locals, we can have to throw a borrow in there. Borrow or borrow mute, but I think that compiles away, doesn't it? What did I finish reading? Okay, yeah, this initializes the next available local in the compiler's array of variables. It stores the variable's name and the depth of the scope that owns the variable. Worried about the lifetime of the string for the variable's name, the local directly stores a copy of the token struct for the identifier. Oh, we're talking about lifetimes in here. Wow, this is C code. Right, so yeah, this is a pointer directly to the token's name. Tokens store a pointer to the first character of their lexeme and the lexeme's length. That pointer points into the original source string from the script or REPL entry being compiled. In our case, the token itself is generated, allocated, and the lexeme that's within it is actually a copy, a clone. So, which is unfortunate. As long as that string stays around during the entire compilation process, which it must since, we're compiling it, then all of the tokens pointing into it are fine. I could rewrite all of this so that we just use that string directly. I don't want to. That seems like a lot of work. Our implementation is fine for a correct LOX program, but what about invalid code? Let's aim to be robust. The first error to handle is not really the user's fault, but more of a limitation of the VM. The instructions to work with local variables refer to them by slot index. That index is stored in a single byte operand, which means the VM only supports up to 256 local variables in the scope at one time. If we try to go over that, not only could we refer to them at runtime, not only could we not refer to them at runtime, but the compiler would overwrite its own locals array too. Let's prevent that. Okay, so we can do that here. If self.locals.borrow.len is equal to, I'm going to say is greater than or equal to 256. Self error, return, self error, too many local variables in function. Okay, that works for me. Yep. The next case is trickier. Consider var a equals first, var a equals second. At the top level, LOX allows redeclaring the variable with the same name as a previous declaration because that's useful for the REPL. But inside a local scope, that's a pretty weird thing to do, and it's likely to be a mistake. And many languages, including our own LOX, enshrine that assumption by making this an error. So in Rust, you can do it, right? It's called shadowing. Oh, interesting. The Rust programming language does allow this, and idiomatic code relies on it. Yeah. Note that the build program is different from this one, right? Because this one is actually in a separate scope from this one. It's okay to have two variables with the same name in different scopes, even when the scopes overlap such that both are visible at the same time. That's shadowing. That's what Rust calls it too, even though it's in the same scope. Called it shadowing. It's only an error to have two variables with the same name in the same scope. So we detect that error like so. So yeah, we have to loop over every variable in the list and looking for it. Don't worry about that odd depth not equal to -1 part yet. We'll get to what that's about later. So we're just looping over each one, and yeah. So, and that happens down here in declare variable. All right, just before we call add local, we check all the locals to see. And what's the easiest way to do this? Identifiers equal. Oh, all we're doing is a string compare. Okay, so we don't even have to, well, we could. I guess we can just say self locals borrow iter. What we're trying to do is compare the name. Oh, that's okay. That's why we get the self parser previous. We get the name that way. Okay, so let name is equal to self parser previous. That's a token, and I did make the Lexeme a pub. Can we just filter like this and say x.lexeme is equal to name count if not equal to 0? Will this work? Self error already a variable with this name in this scope. And we call add local anyway. Once we report the error, we'll stop compilation. I just don't want to do this part. I guess we could. I mean, it doesn't matter. Does that work? Oops. Except name, Alexi. Thank you. Thank you, Rust. That was smart of you. Okay, what's the thing I'm not using is depth. I'm not using depth yet. Here's depth. Here's where we use depth. So we set it, but we never read it, and here's where we read it. Okay, so let me see if, I'm just going to try this real quick to see if this works. Cargo run. Because I have no idea if that's going to work. So we should be able to do this and then say var a equals 1, var a equals 2, and it should complain. It did not complain. So whatever I did was wrong. Add local. I guess I could just dump this out, right? What did I just do there? Print adding name, and we can print out the count. Yep, like that. Borrows iter filter name count, and just see what it is. Cargo run. Let's copy paste. It's not getting there. So we're never, okay. So maybe I just it hasn't been hooked up yet or something. Because I don't see it adding the locals. That doesn't make sense. Oh boy, what did I do wrong? It's already broken. Yeah, we called declare variable twice. Oh, do I have it backwards? If scope is 0, return. So I should be doing not equal to 0. That's what I did wrong. Bang. And then we probably get rid of this println. Nope. Error at open brace, expect semicolon after expression. So maybe... yeah, it should be seeing that right away, right? Uh-oh. Okay, let's take a look at the open brace, left brace. Here. So in the statement, if is match token type left brace, begin scope. So this should be working. Pum. Where's is match? Println is match of T type. Hard to run. Oops. I keep doing that. Well, obviously you need to get this thing working, otherwise it's going to be a problem. Does it match UF? No. Var? No. Print? No. Left brace? Yes. Match var, it's adding A. Oh. Oh, I must have done something weird then. Or maybe doing this typo here caused it to fail. Oh no, okay. That's weird then. Okay, it's working. Yeah, error at A. Already a variables with this name in this scope. Okay, so that's working. I don't know what I did to debug it. But let's get rid of the printlns. I don't like the fact that it's got all spread out. Doesn't this fit on one line? Yeah. Why would it spread that out when you can see it right there? Oh well. Okay. So, where were we? Right, so this is the identifiers equal. So all I'm doing, I change this up a little bit, right? So I'm looping over, I'm iterating over all the locals and counting how many match. And obviously you could break, once you hit identifiers equal, you could just break out of the loop there at that point, or just return or whatever. But this is short enough that I don't think this is going to be a performance issue. We'll see. And it's only happening during compilation, not during runtime. So local variables are appended to the array when they're declared, which means the current scope is always at the end of the array. When we declare a new variable, we start at the end and work backward, looking for an existing variable with the same name. If we find one in the current scope, we report the error. Otherwise, if we reach the beginning of the array or a variable owned by another scope, then we know we've checked all of the existing variables in the scope. Right. To see if two identifiers are the same, we use this. And I'm using just Rust's equality comparison there. Since we know the lengths of both lexemes, we check them first. That will fail quickly for non-equal strings. Lengths are the same, we can do memory compare. Be a nice little optimization if we could check their hashes, but tokens aren't full lock strings, so we haven't calculated their hashes yet. Yeah, so we don't even have to do this, right? Oh no, it is a vector instead of a hash map. We could have just, if it were a hash map, we could have just stored it that way. With this, we're able to bring variables into being, but like ghosts, they linger on beyond the scope where they are declared. When a block ends, we need to put them to rest. So in end scope, after we subtract one from the depth, we need to pop all of op pop, while self.locals.borrow.len is greater than 0, and self.locals.borrow dot of the count dot last dot unwrap dot depth is greater than self scope depth self emit byte op code pop self locals borrow mut pop. Is that going to run into borrow checking issues? No? Into. No. Okay, that worked. And now we got rid of that last warning because we're actually reading depth. When we pop a scope, we walk backward through the local array looking for any variables declared at that scope depth we just left. We discard them by simply decrementing the length of the array. There's a runtime component to this too. Local variables occupy slots on the stack. When a local variable goes out of scope, that slot is no longer needed and should be freed. So for each variable we discard, we also made an op-pop instruction to pop it from the stack. When multiple local variables go out of scope at once, you get a series of op-pop instructions that get interpreted one at a time. A simple optimization you could add to your locks implementation is a specialized op-popping instruction that takes an operand for the number of slots to pop and pops them all at once. So we can now compile and execute local variable declarations. At runtime, their values are sitting where they should be on the stack. Let's start using them. We'll do both variable access and assignment at the same time since they touch the same functions in the compiler. We already have code for getting and setting global variables, and like good little software engineers, we want to reuse as much of that existing code as we can. Something like this. Instead of hard-coding the bytecode instructions emitted for variable access and assignment, we can use a couple of C variables. First, we try to find a local variable with a given name. If we find one, we use the instructions for working with locals. Otherwise, we assume it's a global variable and use the existing bytecode instructions for globals. All right, so we have set global or get global. We're going to call this resolve local function. So we can say let get op and set op equal self resolve if self resolve local and then current. It gets current. Self current. Guess we can do that. Maybe. Hopefully it doesn't. Yeah, we'll have to make sure that this is a immutable function, and then name. Is equal to -1. I see. I see. What we're doing is we're getting the arg based on whether or not resolve local. We either get this arg here, and what does identifier constant return? It returns a U8. So we're not going to be able to get -1 out of that. So what we need to do is have resolve local return an option U8. I think that's the best approach. Blisky-san, thank you for the follow. So yeah, if resolve local returns an option U8, then we'll be able to say if it's some. And otherwise set arg to the identifier constant here. So we can say if, let's try it this way, if let sum arg equals resolve local self current name Oh, and then arg is only going to be valid for that scope. So we're going to say let local arg get op and set op equals this. Then we're going to return local arg get op set op. And that's going to be U8, so that'll be just copy thing. And then else, we're going to do self identifier comma, and then this is going to be set local and get local, right? Opcode get local and opcode set local. Otherwise, it's going to be opcode get global or set global, like that. And then we're going to pass this as set op and this as get op. Now can we make it even simpler than that? Uh-oh, didn't like this. Oh, we don't have resolve local yet. We can fix that. Get op. What's it complaining about here? Oh, self parser current. Okay, we solved 3. Oh, we don't have a get local or set local. Okay, good. Okay, we're getting there. Right. First, we try to find a local variable with the given name. If we can find one, we use the instructions for working with locals. Otherwise, we assume it's a global variable and use the existing bytecode instructions for globals. A little further down, we use those variables to emit the right instructions, right? So we're going to do emit bytes, set up, or get op, depending on. And for access, and notice it's being cast. So I bet you it's returning, it's returning an int. So we're going to actually not do that. We're going to return an option. So we'll say fn resolve local. We're going to take a non-mutable reference to self and a pointer to the token. And we're going to return option U8, like that. Oh boy, we're getting all these people. There we go. Okay, and now for resolve local, we're going to do the same thing we did for trying to find a predefined local, except we want to find the one and only thing that's there. So we should be able to do the same filter, right? But instead of getting the count, we should be able to just take one. And there should be one. Oh, there might not be one. Right? So does take one return a sum? Rust filter. No, we want to do take one, like that, right? This is next. How does this? Oh, this is the okay. What am I trying to look for here? In iter. So Rust iter take one. Let's look for an example. Oh, first. That's interesting. There's a last. There's no first for vectors. Okay, I don't care. Rust iterator cheat sheet. Take while. Yeah, I just want to take one take. and it returns a take. Okay, yeah, and then you have to call next on it, and to get the sum or the none. But that's not returning the depth, right? I want to get the index of it, so that's not going to help. Okay, so for E, V in self locals borrow, iter enumerate. I guess this is the best way to do it. If v dot name dot lexeme equals name dot lexeme, return sum E. None. This seems like a boring way to do it. I was hoping there'd be a nice clean way to do it. Oh, fine. Wait. Expected 1 argument and got 2. We don't need to pass in the compiler, right? Yeah. What am I passing in here? This says compiler. Current. Oh, right, yeah. So we get that for free. And we still don't have get local and set local. Okay. So this works, although it's ugly. I would very much like to do a better version of that, but anyway. For all that, it's straightforward. We walk the list of locals that are currently in scope. If one has the same name as the identifier token, the identifier must refer to that variable. We found it. We walk the array backward. Right, you have to walk it backwards. Reverse iter. So reverse iter. Rust reverse iter. Iter rev. Oh, and then does the enumerate go the wrong way? Right, because now we're walking it backwards, but we're going to refer to this. So this should be length minus E as U8. Oh, man. Self locals borrow len minus -1. Okay. I have no idea if that's correct. We'll find out when we try to test it. That ensures that inner local variables correctly shadow locals with the same name and surrounding scopes, right? That's why you have to go backwards. At runtime, we load and store locals using the stack slot index. So that's what the compiler needs to calculate after it resolves the variable. Whenever a variable is declared, we append it to the locals array in the compiler. That means the first local variable is index 0, next one's at 1, and so on. In other words, the locals array in the compiler has exact same layout as the VM stack will have at runtime. The variable's index in a local array is the same as its stack slot. How convenient. If we make it through the whole array without finding a variable with the given name, it must not be a local. In that case, we return -1. In our case, we're returning none to signal that it wasn't found and should be assumed to be a global instead. So now we're going to have to add in chunk. We have get global and set global, get local and set local. Add them both now. There we go. Its implementation in VM. Get global and set global. I guess we can just, oh, that's right after pop. Sure, why not? Op code get local is read byte. Ooh. I don't think I have that, or something similar to that. I do. Okay, I do. It's been a while. And it returns Oh, this returns an opcode. So where is read byte used? That's the instruction. So I should do it the other way around, right? Opcode like this. Into. And then this should just return a U8. And then get local, we'll say let slot equals self read byte. And then push self dot stack dot push VM stack slot. VM stack, oh, self stack, slot. That's not going to work, right? Slice indices, or I can do it as usize. I don't know if that's going to work because of the okay, set local is going to be opposite. Let's do this part here so the compiler doesn't complain at me. Get local. It's a byte instruction. Op get local offset and then set. And then we're going to have to write byte instruction as a thing. So fn byte instruction self. We don't need the chunk, and then we just need offset usize as usize. So we say let slot is equal to self code offset plus 1. Println. We still do. Oh, we don't have the name. There, now we do. Minus 16. And then we're going to do 4D on the slot. Just like that, right? And return offset plus 2. So it's almost the same as the constant instruction, except the constant instruction also decodes the constant that it points to. Okay. And now we don't have the actual instruction for set local, which we can add right after get local. And that's going to be self let slot is self read byte as usize. And then we're going to say self stack of slot is equal to self peak of 0 dot clone. Move occurs. Clone. Ooh, wow, it compiles. All right, so I blasted through all of that, didn't I? So our compiler is emitting 2 new instructions, so let's get them working. We did get the get local. Its implementation looks like this. It seems redundant to push the locals value onto the stack since it's already on the stack lower down somewhere. The problem is that the other bytecode instructions only look for data at the top of the stack. This is the core aspect that makes our bytecode instruction set stack-based. Register-based bytecode instruction sets avoid the stack juggling at the cost of having larger instructions with more operands. So this takes a single byte operand for the stack slot where the local lives. It loads that value from the index and then pushes it on top of the stack where later instructions can find it. So next is assignment. You can probably predict the implementation. It takes the assigned value from the top of the stack. It peeks it, right? Doesn't pop it. And stores it in the stack slot corresponding to the local variable. Note that it doesn't pop the value from the stack. Remember, assignment is an expression, and every expression produces a value. The value of an assignment expression is the assigned value itself. So the VM just leaves the value on the stack. Right, so I mean, it's the equivalent of doing a pop into there and then pushing the result of the assignment back on, which means just do a peek. Our disassembler is incomplete without support for these two new instructions. The compiler compiles local variables to direct slot access. The local variable's name never leaves the compiler to make it into the chunk at all. That's great for performance, but not so great for introspection. When we disassemble those instructions, we can't show the variable's name like we could with globals. Instead, we just showed the slot number. Erasing local variable names in the compiler is a real issue if we ever want to implement a debugger for our VM. When users step through code, they expect to see the values of local variables organized by their names. To support that, we need to output some additional information that tracks the name of each local variable at each slot. So can we do this now? Cargo run. Var a equals foo, print a. It was able to get the local and push it onto the stack. We still had the foo, and then we have the pop instruction for the close brace. And in fact, if we do var a equals 1, var b equals 2, var c equals 3, print a times b times c, it generates 3 pops. Outputs the 6 correctly and then generates 3 pops. There's get local 0, get local 1, get local 2. So we are looking it up correctly. I was worried that my little for loop with the reverse and the iter and the whatever wasn't going to work, but it worked. So that's good news. Let's clippy this. Let's finish the edge case here and then call it a stream. Oh, that's it. That's the whole chapter. All right, let's finish this. We already sunk some time into handling a couple of weird edge cases around the scopes. We made sure shadowing works correctly. We report an error if 2 variables in the same local scope have the same name. Hopefully I didn't break that. Yes, okay. For reasons that aren't entirely clear to me, variable scoping seems to have a lot of these wrinkles. I've never seen a language where it feels completely elegant. No, not even Scheme. We've got one more edge case to deal with before we end this chapter. Colossal Hitchhiker, thank you for the follow. Recall this strange beastie when we first met in JLox's implementation of variable resolution. Right, I remember that. We slated then by splitting a variable's declaration into 2 phases. We'll do that again here. So we declare uninitialized and then ready for use. As soon as the variable declaration begins, in other words, before its initializer, the name is declared in the current scope. The variable exists, but in a special uninitialized state. Then we compile the initializer. If at any point in that expression we resolve an identifier that points back to this variable, we'll see that it is not initialized yet and report an error. Okay, after we finish compiling the initializer, we mark the variable as initialized and ready for use. So to implement this, when we declare a local, we need to indicate the uninitialized state somehow. We could add a new field to local, but let's be a little more parsimonious with memory. Frugal? Yeah, frugal. Instead, we'll set the variable's scope depth to a special sentinel value, -1. Oh boy. But I made depth the usize. Isn't that exciting? So the right way to do this in Rust would be using an option. Right? To indicate that the depth exists. But that's going to make our loop funky. This loop here, because if these are all options, and then we call mark initialize, which will modify the depth. After it's been... Oh, that's annoying. Isn't that annoying? Because we have to do this stack-based -1 local count thing. Blah. All right, so here's depth. Here's depth. Here's depth. Let's see how bad it looks with an option. Oops. How much does this hurt by making it an option? We can just assume an unwrap because we're checking the length here. Make sure it's greater than 0. And this becomes none. Right? Then, in define variable, else self mark initialized. Yuck. Okay, fn mark initialized. And this requires a mutable reference to self, which we already have, so that's okay. And it's going to just assume that the last one, self, locals, borrow, mut, last, depth equals sum, self, scope, depth. Will this even compile? Unwrap. Nope. Cannot assign. Oh, do I have to just put a star in front of it? Nope. Option use size cannot be dereferenced. If let sum local equals this. And local dot depth is that. Is that going to work? Nope. Call TwitchBot. Thank you for the bits. This expression has ampersand local, expected a local, but found an option. Oh, because I did the unwrap. Local is an ampersand reference. Help changing this to mutable reference. Okay, let's see if that works. Nope. Type's different immutability. I'm borrowing mute. Dang it. I guess I could just borrow the full locals. Not this way, though. And this is going to be, you can't do this because it's only temporarily borrowed. Locals of local len -1 equals sum self scope depth. And that's going to complain that we can't do that. Ooh, expected struct local. Oh. Yeah, because we haven't gotten to the borrow checker yet. Cannot borrow locals as mutable as not declared mutable. Oops. And so we have to grab the length here. Let len equals locals len -1. Self locals. Borrow. Oh, wow. I can't believe that worked. I can't believe that worked. I don't want to call this len, though. I want to call it last. Okay. I think that did the trick. Oh, we have to change this here and resolve local. Okay. Once the variable's initialized is being compiled, we mark it initialized. Right. That's implemented like so, and that's what I just hammered out there. Right, so if I cargo run now, bar A equals A. Panicked. Yeah. And that's on VM line 85. Yeah. Okay. We haven't gotten to the error. Okay, so here, right. So this is where we do it. This is really what's declaring and defining variable means in a compiler. Declaring is when the variable is added to the scope and defining it when it becomes available for use. When we resolve a reference to a local variable, we check the scope depth to see if it's fully defined. So that is in compilers. Resolve local. If they're equal, if self dot uh-oh. We have this local here. I don't remember what that was now. Is that the V? V dot depth is none. Self error can't read local variable in its own initializer. Else. Oh, I guess we don't want else. We can just return an error out there. Right? Let's try that. Nice! It works! Perfect! So we can see here it failed. Here it passed it. It'd be nice to, if I had the brain power, I could write this all test-driven development. If the variable has a sentinel depth, or none in our case, it must be a reference to a variable in its own initializer, and we report that as an error. That's it for this chapter. We've added blocks, local variables, and real honest-to-God lexical scoping. Given that we introduced an entirely different runtime representation for variables, we didn't have to write a lot of code. The implementation ended up being pretty clean and efficient. You'll notice that almost all of the code we wrote is in the compiler. Is it? Probably. Wow, that's a lot of changes. Let's check in with Clippy really quick. Okay, git add source. Git commit -m. Oh, git log. What do we have? 21.4. Okay, so this, all of chapter 22 is done. Right, this is chapter 22? Yeah. Git commit -m chapter 22 local variables. Over in runtime is just two little instructions. You'll see this as a continuing trend in CLOCs compared to JLOCs. One of the biggest hammers in the optimizer's toolbox is pulling work forward into the compiler so you don't have to do it at runtime. In this chapter, that meant resolving exactly which stack slot every local variable occupies. That way, at runtime, no lookup or resolution needs to happen. You can look at static types as an extreme example of this trend. A statically typed language takes all of the type analysis and type error handling and sorts it out during compilation. Then the runtime doesn't have to waste any time checking that values have the proper type for their operation. In fact, in some statically typed languages like C, you don't even know the type at runtime. The compiler completely erases any representation of a value's type, leaving just the bare bits. Okay, so let's push this up. Git push. I think it's this tab here. Yeah. All right, so we finished chapter 21 and we finished chapter 22. Nice. Over our simple local array makes it easy to calculate the stack slot of each local variable, but it means that when the compiler resolves a reference to a variable, we have to do a linear scan through the array. Yeah. Come up with something more efficient. Do you think an additional complexity is worth it? I guess the additional or the alternate implementation would be a hash map. And when you insert something into the hash map, you just take the current hash map's size as the index into the array. How do other languages handle code like this? What would you do? We already asked that, and we didn't answer it. Many languages make a distinction between variables that can be reassigned and those that can't. In Java, the final modifier prevents you from assigning to a variable. In JavaScript, the variable declared with let can be assigned, but one that declared using const can't. Swift treats let as a single assignment and uses var for assignment variables. Scala and Kotlin use val and var. Pick a keyword for single assignment variable formed at blocks, justify your choice, then implement it. I would probably just use const. That's the most straightforward in my brain. Constant. An attempt to assign a variable declared using your new keyword should cause a compile error. I'm not going to do it though. Extend clocks to allow more than 256 to be in scope at a time. I'm not going to do that either, but I understand how to do it because we already discussed how to do that for constants in a previous chapter. Speaking of chapters, the next chapter is going to be jumping back and forth, and we'll tackle that tomorrow. So thank you everyone for hanging out with me and watching me work my way through this book. I'm having a lot of fun. I hope you're enjoying it too. And I will see you tomorrow for jumping back and forth. All right, take care everyone.